to MathStat341, lecture 23. What we're going to be doing today is we're going to continue with our study of different random variables. We're going to look at a lot of chi-squared random variables today. And I'm going to start off by proving something you should have already seen, the Pythagorean theorem. There are a tremendous number of different proofs of the Pythagorean theorem. Only one US president is credited with a proof of the Pythagorean theorem. Who is this US president?
Garfield.
It is Garfield. Some people may think his proof is highly derivative of another proof, but he is given credit for a trapezoidal proof of Pythagoras. There's lots of different proofs. If there's time at the end of today, I'll talk about a few more. So a squared plus b squared is c squared. I want to show you a different proof. I want to show you a proof by dimensional analysis. Do you agree that the area is a function of the hypotenuse and the angle? That if I give you any triangle, as soon as I specify the angle and the hypotenuse, the other sides are determined, so the triangle is determined, so the area is determined. And if you want, A is just going to be C cosine theta, and B is just going to be C sine theta. If I triple C, what happens to the area? The area triples if I triple C?
I think it goes 9.
It goes up by 9.
Yeah.
So we know that this has to be of the form c squared times f of theta for some function. Now, any good geometry proof has, at some point, an auxiliary line that must be drawn. So we need to draw an auxiliary line to this triangle. Where should we draw that auxiliary line? And remember, we like right triangles. We're trying to study right triangles. Where would be a good place to draw this line?
Right down through the right angle so you can get to a right triangle.
Okay, like this. And I'm going to give these triangles the great names 1 and 2. Okay? Now, in triangle 1, what's the hypotenuse of triangle 1? So it's going to have area a squared f of theta. What about the area of triangle 2? What's its hypotenuse?
B squared.
B. And if this is theta, this is 90 minus theta, so this is theta over here. And the area of the whole triangle is just c squared f of theta. And since these two fit together, you have a squared f of theta plus b squared f of theta equals c squared f of theta. What can we conclude?
A squared plus B squared.
Is there anything we need to do to be able to conclude that, or can we conclude this immediately?
We need to make sure f of theta is not 0.
So we'll just write note f of theta is not 0. If f of theta was 0, it would mean the triangle would have 0 area. And this is a nice proof of the Pythagorean theorem. It comes down to the fact that area is going to be length squared. The reason I want this is I want us to be thinking about dimensional analysis, because later today we will be dealing with generalizations of spherical coordinates to n-dimensional space. I do not want to ask if you remember your spherical coordinates from Calc 3. Primarily not because I have any doubt that you remember them, but because the mathematicians and physicists have different notations as to is it theta or phi coming down from the z-axis, and I don't want to get into a fight. But what do you think it's going to look like if we now have n-dimensional space? What are the spherical coordinates going to look like? How do we generalize that? We can actually bypass a lot of this, and that's the whole goal. It's to continue integrating without integrating. All right. So this was the Pythagorean theorem. So we've already done a little bit with the gamma function. I'm going to just state a few quick things. So the gamma function. And it's defined as gamma of s is the integral from 0 to infinity of e to the minus x x to the s minus 1 dx. Sometimes it's written 0 to infinity, e to the minus x, x to the s, dx over x. They're of course equivalent. The reason we sometimes write it this way is if I rescale x by 7, dx over x is unchanged. And this is just a good way of thinking about what's going on. It turns out to be related to like a Mellin transform of the exponential function. There's a lot of big theory lurking here. Whenever you have something like this, you always want to ask, does the integral make sense? Does it converge? So the two troublesome points are what happens as x goes towards 0, what happens as x goes to infinity. Well, what's nice is as x goes to infinity, exponential death kills any polynomial growth. So if we want to look at the limit as x goes to infinity, let's say we had x to some power divided by e to the x to see which wins. So you have infinity over infinity. What do? L'Hopital. And if you still have infinity over infinity, what do? L'Hopital. And you keep doing L'Hopital, and eventually you get the limit as x goes to infinity, if m is an integer, m factorial over e to the x. So the exponential function is decaying faster than any polynomial. So if x is like 2019, this is decaying faster than x to the 3,000, than 1 over x to the 3,000. So I'm going to have clearly enough decay. So I can make x to the s divided by e to the x. I can make this less than equal to x to the negative 2,000 for x large. So I can have plenty of decay. The issue is what happens near 0. What does e to the minus x look like when x is near 0? It looks like 1. So the problem is near 1, I have the function x to the s. I'm sorry, x to the s minus 1. So near 0, the integrand is approximately x to the s minus 1. When is that going to be integrable? What do I need about s? So when will x to the s minus 1 be integrable?
Oh, s minus 1 has to be positive.
So I need s minus 1 to be greater than 0, or I need s to be greater than 1. So as long as s is greater than 1, if I have 1 over square root of x, 1 over square root of x blows up, but it is integrable. So for example, if I have the integral from 0 to 1 of x to the minus a half dx, this is x to the 1/2 over 1/2, and that's finite. It's well behaved. But if I try to do the integral from 0 to 1 of x to the minus 1 dx, this would be the natural log of x at 0 and 1, and you would have the log, okay? And if it's even less than negative 1, if it's negative 2, it's even worse. Now, I'm writing here s, and we're doing things with s as real, but you can actually generalize s to complex numbers. And it just matters what the real part is. It's just worth being aware of this. If you do the calculation, what is the easiest value of s to put in? No, 1, right? Because if you put in 1, you get x to the 0. So if you put in s equals 1, and you do the calculation, you get 1. The next easiest one is when you put in 2. And when you put in 2, you get 1. So no matter what positive integer I put in, I always get 1. Okay, probably not. Let's try gamma 3. And I get 2. Okay, it must be the Fibonacci numbers, 1, 1, 2. I try the next number, and I get 6. And I try the next number, and I get 24. And again, you can prove all of these by integrating by parts. This is a good way for you to check your integration theory. Does anybody recognize the numbers 1, 1, 2, 6, 24? Yeah, these are factorials. This is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. The gamma function generalizes the factorial function. It agrees with the factorial function at the integers, but takes on other values elsewhere. And so, as an exercise, you can show gamma of s plus 1 is s gamma of s. And this is integrate by parts. So I will leave that as an exercise for you to do. Another identity you can prove is gamma of s, gamma of 1 minus s is, I think it's pi s. I'm make sure I get this right. No, just pi, although I think sine of pi s. And what's interesting is the way you prove this is you write each one of these as an integral. And this is very similar to the issues we had when we had sums of two uniform random variables. We had to be very careful where things are defined. If I'm doing my integral, I need s to be what? Greater than 1. Right? But then if I look at gamma of 1 minus s, wait a minute. Wait, it's not s minus 1 is greater than 0.
Oh, it's greater than negative 1.
It's greater than negative 1. I should have realized that. Sorry. So it's s minus 1 is greater than negative 1.
Can we not write greater than equal to?
Oh, yeah.
No, we can't write greater than equal to. Because if it equals negative 1, you have 1 over x, which we showed integrates to logarithm. So we need s to be greater than 0. Sorry. So when we look over here, we can write this as an integral. We need s to be greater than 0 here. Over here, what do we need s to be? Less than what? Less than 1. So we can write these out as integrals as long as s is between 0 and 1. And we can prove this relationship for values of s between 0 and 1. And then there are techniques that allow us to extend this to all values of s from those. It involves complex analysis. So for those of you who are thinking of being a math major or thinking of going to grad school in mathematics, complex analysis is a wonderful class. Looking at this formula, however, there is one particular value of s which if you listen to, it's saying, please, please choose me. Which value is that?
1/2.
1/2. Because then s and 1 minus s are the same. So you get gamma of 1/2 squared is pi over the sine of pi halves, which is 1. So gamma of 1/2 is the square root of pi. And if you want, this is the same as negative 1/2 factorial is the square root of pi, if you consider the generalization of the factorial function. Right. The last thing I want to remark about this, I think this is going to be. So let's look at the expected value of x to the, I'll do 2m, where x is normal 0, 1. So this is going to be the integral from from negative infinity to infinity of x to the 2m, 1 over the square root of 2 pi e to the negative x squared over 2 dx. This is the same as twice over square root of 2 pi, the integral from 0 to infinity, e to the negative x squared over 2 x to the 2m dx. I'm not calculating the odd moments because I know the odd moments is 0. What does this kind of look like? Kind of. Not perfect, but kind of. It looks a little bit like the gamma function. So let's let u be x squared over 2. So du, the 2's cancel, will just be x dx. So that means dx is going to be du divided by x, but x is equal to the square root of 2u. So this would be 2u to the negative 1/2 du. Right? So we get that the expected value of x to the 2m is just going to be 2 over the square root of 2 pi, integral from 0 to infinity, e to the negative u. Now x to the 2m, well, x squared is 2u, so this will become 2u to the m, and then we'll have a 2u to the minus 1/2 du. Right? Isn't this looking a lot like the gamma function? All that I have to do now is I need to have a u to an s minus 1. So I can write this as, I'm not going to bother getting into that. So I'll have a 2, I'll have a 2 to the m from this. I have a 2 to the negative 1/2, so that 2 down below, oh, that 2 cancels with that, so that 2 is going to cancel with that. I'll have a square root of pi over here. I'll have an integral from 0 to infinity. I'll have an e to the minus u, and I have a u to the m minus 1/2. So I'm going to write that as a u to the m plus 1/2 minus 1 du. And now, this is just going to be 2m over square root of pi, and that's just going to be the gamma function at m plus 1/2. If we take m equals 0, then we get 2 to the 0 is 1, square root of pi, so we get gamma of 1/2 over square root of pi. Yes, that does equal 1. It is the normalization constant. If we take m equals 1, you have to do a little bit more work, but it will give us the second moment. So the even moments of the Gaussian can be interpreted in terms of values of the gamma function at half integers. So this is just trying to show you what a wonderful function the gamma function is, how it surfaces in some really important places. Okay. We can use the fact that we have the integral of the gamma function to create new probability distributions. So all the stuff here is done in detail in the book. Right? It's going to be a lot of painful integration, and as much as possible I will try to integrate without integrating. Okay? So we're going to define the gamma the chi-square distribution. With new degrees of freedom. So how many of you have seen the chi-square distribution before? Okay. So I want to make sure I define it correctly. So the density, maybe new down here, is going to be 2 to the new halves, gamma to the new halves inverse, I think? Yep, new halves inverse, x to the new halves minus 1, e to the negative x halves, to x greater than or equal to 0, and 0 otherwise. Okay?
A lot of terms.
I'm sorry? Yes.
There's a lot of terms stuck together.
Yes. And when you look at this, you go, really? It's new halves occurring everywhere. Why don't we say this is a chi-square distribution with new halves degrees of freedom? It turns out it's more useful to view it as new degrees of freedom. And new is often going to be an integer, but it doesn't have to be. So the first thing you need to do is you need to show it integrates to 1, and then you need to show it's non-negative. Non-negative isn't hard, right? To show that it's non-negative, well, everything in sight is non-negative. You need to show that it integrates to 1. Well, doesn't this look a lot like the gamma function? The problem is that it's an e to the negative x halves, not an e to the negative x. Remember, gamma of s is the integral from 0 to infinity, e to the minus u, u to the s minus 1 du. And so unfortunately, the way the chi-squared is defined, you have an x halves. We don't have so we do a change of variables. We let u equal x halves. And so after algebra and calculus that's in the book, it does integrate to 1. And in fact, almost surely, that's why we have the 2 to the new halves, gamma new halves inverse. And it's not surprising that you see a gamma function coming into play. And it's not surprising that you have a nu over 2, because we saw that we were going to have to do a change of variable. So again, whenever possible, you want to see, is my answer reasonable? Does it seem to match what's going on? All right, so this is the chi-squared random variable. So there's a lot of different theorems about it. So we have 3 theorems. Theorem 1, if x is normal 0, 1, then x squared is a chi-squared distribution with 1 degree of freedom. So this is the Greek letter chi. So that's our first theorem. Theorem 2, if the xi's are all normal 0, 1, then x1 squared plus xn squared is chi squared with n degrees of freedom. And theorem 3, if yi is chi squared with nu I degrees of freedom, then y1 plus yn is chi squared with nu 1 plus nu n degrees of freedom. So these are 3 great results. The square of the standard normal is a chi-squared. The sum of the sum of squares of standard normals is a chi-squared, and the degrees of freedom is just the number of terms you have. And the last is that if you have a sum of chi-squared random variables, of course everything is independent, then their sum is also chi-squared. Yes?
Is the second one like a special case?
So the second one is a special case. Because if I just choose yi to be the square of a standard normal, well, we know by the first case, that's what this would be. So we could actually get theorem 2 immediately from theorem 1. And for theorem 3, we only have to do the case when n equals 2. Because if we know if the sum of 2 chi-squareds is chi-squared, then if we had 3, we would do grouping. We can do the standard trick we always do. y1 plus y2 plus y3. You first group that. And that would be a chi-squared with nu 1 plus nu 2. This is a chi-squared with nu 3. So the sum is a chi-squared with nu 1 plus nu 2 plus nu 3. So we really only have to do theorem 3 in the special case when n equals 2. And we get it for any finite n. Okay, so there's a couple of ways we can start to do a lot of these calculations. We can start trying to use our CDF method, write down our new variable, try to calculate things, and go through and do all of that. So I'm just trying to see which one I want to do. And so I'll start off with doing theorem 1. All right, so for theorem 1, let's let y be x squared, where x is normal 0, 1. So the probability that y is less equal to little y is the probability that x squared is less equal to 1. So this is a way to just review the CDF method, which is a wonderful technique for calculating. All right, well, this is the same as the probability that negative square root of y less than equal to x less than equal to square root of y. We have to be very careful. So this is the cumulative distribution function of big Y evaluated at little y. And this is the same as the cumulative distribution function of x evaluated at square root of y minus the cumulative distribution function of x evaluated at negative square root of y. What makes the CDF method work so well is we do not need to know what the CDF is. What are we going to immediately do? So what do we do now? differentiate. And so we now get the density, and now it's the derivative of this at square root of y. And then we have to remember to take the derivative of square root of y, which is going to be 1/2 y to the minus 1/2. And now we take the derivative of the other piece, so it'll be at negative square root of y. And the derivative of negative square root of y is going to be negative, so the negative and negative becomes a positive, 1/2 y to the minus 1/2. But the density of the standard normal is symmetric about 0. So the value of y and square root of y is the same, right? So this is going to just be twice this, so that cancels the 1/2. So you get fx at square root of y to the minus 1/2. So this will be 1 over square root of 2 pi e to the negative square root of y squared over 2. So it'll be y over 2. And then we have y to the minus 1/2. Right? And so I'm going to write y to the minus 1/2 as y to the 1/2 minus 1. And now you can see, boy, does that look a lot like this. The only thing that's different is I've got to remember now that gamma of 1/2 is the square root of pi. And that's where that is coming from over there. And then so do I have the 2 in the wrong spot? Let me just check, because I'm wondering if I actually just put the 2 in the wrong spot. So did I drop them? Oh yes, I apologize. I dropped a negative 1 over here. Because I could tell that there's got to be a mistake because this is clearly correct, and I've got the 2 down below. So apologies. I dropped the minus sign over there. So we've shown now that the square of a standard normal is a chi-squared. So for those of you who are doing statistics, a lot of times you assume errors are normally distributed. And when we do things like the method of least squares, we're going to square errors because we don't want signed errors to cancel. So understanding sums of squares of normal random variables is extremely important. All right, so we only have to do theorem 3 in the special case when n equals 2. Right. Any questions in terms of what we've done up till now? The details are all in the book. This is just a lot of algebra to see. But it's just, you follow your nose, it's the PDF, it's the CDF method. We don't need to know a closed form, thank God, because we immediately differentiate. Okay. Any questions on this? Has everybody written this down? Can I regain this board space here? Okay, excellent. I want to try to keep the statements of the 3 theorems. So what I want to do now is I want to prove the second one without proving it. Or what do I mean by that? Without doing painful integration. So, theorem 3. Let's say y1 is chi-squared mu1, y2 is chi-squared mu2. And we want to look at y, which is y1 plus y2. So the density, we're going to have to use the convolution. It's the integral from minus infinity to infinity, the density of the first one, we'll call it at t, and the density of the second one at y minus t dt. All right, well, the chi-squared random variable only takes on positive probability if the argument is non-negative. So from this, what do we know about t? We only have to worry about t that is
T has to be greater than 0.
greater than or equal to 0. And over here, we need y minus t to be greater than or equal to 0, so we need t to be less than or equal to y. So what I get is the following. This is the same as the integral from 0 to y. Now I'm going to do the first density. I don't know about you, I don't really want to write 2 to the negative nu 1 over 2 gamma to the nu 1 over 2 inverse. I'm going to just call that constant c nu 1. It's normalization constant. And then the part that really matters is I have t to the nu 1 over 2 minus 1 e to the negative t over 2. Now let's look at the second one. I'll have its normalization constant c nu 2. Now I've got y minus t to the nu 2 minus 1, nu 2 over 2 minus 1, e to the negative y minus t over 2 dt. Okay. I think it actually still fit on the screen. Amazing. Okay. Let's pull some things out. I can pull out the c nu 1, I can pull out the c nu 2. E to the negative t halves, oh, e to the positive t halves, that's nice, they cancel. We have an e to the negative y over 2 that doesn't depend on t, I can pull that out. And I'm left with the integral from 0 to y of t to the nu 1 over 2 minus 1 times y minus t to the nu 2 over 2 minus 1 dt. And nu 1 and nu 2 don't even have to be integers. Have fun, right? This is a Calc 1 integral. I don't want to do it. But, and this is the whole point, we don't have to evaluate this perfectly. All we have to do is figure out how does this integral depend on y? Because this is a probability distribution, it integrates to 1. I just need the y dependence. Now y, I would love to pull this y out of the integral. I can't. Why can't I pull this y out? Because it's not multiplying t. So screw that. Let's let t equal u times y. And so now dt is going to be u dy. T goes from 0 to y. So what does u go from? So t goes from 0 to y.
0 to 1.
0 to 1. Oh, isn't that much better? We no longer have an integral where y is in the upper bound. So when we put this in, we now get, compacted by this, e to the minus y minus t over 2 dt. We now get that it equals c nu 1, c nu 2, e to the minus y halves, the integral from 0 to 1. Now I replace t with uy, so I'm going to have uy to the nu 1 over 2 minus 1. Now this over here, I'm going to get y minus y times u, right? So I can write this as y times 1 minus u to the nu 2 over 2 minus 1. And then dt is just u dy. Sorry. It's y du. It's y du. So it would just be y du. Okay? Sorry? It's going to be nice. So I'm going to get c nu 1, c nu 2. I can pull out the y, e to the minus y over 2. Now here I have a y to the nu 1 over 2 minus 1, a y to the nu 2 over 2 minus 1. So I'm going to get a y to the nu 1 plus nu 2 over 2 minus 2, plus 1 is minus 1. So actually, this is just y to the nu 1 plus nu 2 over 2 minus 1, e to the minus y over 2, integral from 0 to 1, u to the nu 1 over 2 minus 1, 1 minus u to the nu 2 over 2 minus 1 du. Call that constant c. It's some number independent of y. So it's c nu 1, c nu 2, y to the nu 1 plus nu 2 over 2 minus 1, e to the minus y halves. This over here is the functional form of a chi-squared with nu 1 plus nu 2 degrees of freedom. So this has to be c of nu 1 plus nu 2. You can do the integration out directly, but there's no need. We don't have to evaluate this integral. Conversely, we can now figure out what this integral is precisely because we know it's a probability distribution. And this is one way to evaluate certain difficult integrals. Show that the normalizations of a probability distribution that you understand. If you've seen beta distributions, this is where you get a beta distribution. Okay, there's a lot that we've done so far, and we have a lot more to go. This is the integration day. You're trying to get it all in one day, okay? Go home, slowly look at this and digest this, but it is remarkable that at the end of the day, we don't have to do any of these painful integrals. Once we can establish the functional form, we win. Because it has to integrate to 1. So this gunk over here has to be what we need. All we have to do is we have to do the integration well enough to detect the y dependence. Okay, any questions on what we've done so far? So we've now proven 3, and since we've proven theorem 3, we now have theorem 2. Okay? I want to do theorem 2 another way. I want to do it directly. And by doing it directly, I want to be able to get some interesting consequences. Okay? Everybody comfortable with what we've done so far? The more times you do this, the easier it is. It really takes a while to see how should you look at things. The key insight was we had a y minus t. If t was just y times something, we could pull out the y. And that's the suggestion. That's the good normalization. That's the good change of variable to do. All right. So each xi is normal 0, 1. Let's let y be x1 squared plus xn squared. Okay? We want to calculate what's going on. We could try to do this with a multiple convolution. Yeah. X1 squared plus x2 squared convolution for the... Right? Let's try to do things directly. It's nice to see lots of different ways of doing things. Let's say we want to calculate the probability that y is less than or equal to little y. This is the same as the probability x1 squared plus xn squared is less than or equal to y. Well, we know what the probability density is for each one of these. What is this shape x1 squared plus dot 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 plus xn squared plus equal to y? What shape is that? It's a...
Normal or chi-squared?
No, which shape? x1 squared plus dot 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 plus xn squared is less equal to y. Geometrically, what shape is that? If I told you x squared plus y squared plus z squared is less equal to 5, what shape is that?
Oh my god. A sphere.
It's a sphere. So this would be an n-dimensional sphere. So this is the same as the integral x1 squared plus dot 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 plus xn squared less equal to y. So it's a sphere of radius square root of y, or an n-dimensional sphere. 1 over square root of 2 pi to the n, e to the negative x1 squared plus xn squared over 2. dx1 through dxn. That's what we need to integrate. And then we need to then take the derivative of this with respect to y. But we're just integrating over the probability space where the sum of the squares is at most y. Okay, so you remember your spherical coordinates with the sines and the cosines and the products of the sines and the cosines? We now need n-dimensional spherical coordinates. So we're going to have theta 1, through theta n minus 1 and some radius r. And now we need the change of variable formula in spherical coordinates. So not only do I have to write down the n-dimensional spherical coordinates, I then have to calculate the Jacobian. Screw that, right? dx1 through dxn, I claim, has to have the following form. R to the n minus 1, some function of the angles, d theta 1 through d theta n minus 1. We talked about this last time when we did things on the circle. When we had r dr d theta, to view that as dr r d theta. That you need to get a length. This is supposed to be n dimension. It should be meters to the n. I know I have to have, oh, I'm missing the dr. I know I have to have d theta 1 through d theta n minus 1 in dr. To get a length to the n, the only way it can work is I have to have r to the n minus 1 to inflate all of those. And then this has to be independent of the radius. This is why I started the day doing Pythagoras. So we have, this equals the integral, r goes from 0 to how large can r go? I think square root of y. Because x1 squared plus xn squared is just r squared. So r squared is at most y, so r is at most square root of y. So r goes from 0 to square root of y, and then we would have the theta crap, right? G of theta 1 through theta n minus 1. Then we would have, the 1 over 2 pi to the n halves. We have e to the negative r squared over 2. That's nice. We have r to the n minus 1, d theta 1, d theta n minus 1 dr. I think I put everything in. And that's the integral we need to do. So the change of variables, there's no angular dependence here because it's x1 squared plus x2 squared plus xn squared. So I don't have to worry about what the spherical coordinates are. This is just going to be r squared. And since r squared is x1 squared plus xn squared, that gives us that r goes up to square root of y for our bounds of integration. When I integrate the theta stuff, it's going to just be some constant. Okay? And in fact, I can incorporate my square root, my 2 pi to the n halves into that constant. It's just some number. And so what are we left with? We are left with some constant, and now all that's left is the r integration. We integrate r goes from 0 to square root of y, e to the negative r squared over 2, r to the n minus 1 dr. And we know this has to be a probability distribution. What does e to the minus r squared over 2 r to the n minus 1 look like? It looks a lot like the gamma function, right? Now we've got to be careful because we're supposed to integrate this now. Do you know how to integrate this? This is painful. So this is equal to the cumulative distribution function at y. Right? So let's say that this cumulative distribution function at y, let's say it's some function, let's call it b at square root of y minus b of 0. What do we immediately do?
Can we take the derivative?
We take the derivative, right? That's the whole point of the CDF method. You never get stuck with the CDF. You only use it and then you take the derivative. So then the density is going to be the derivative of this. So it's going to be b prime square root of y times the derivative square root of y, which would be 1/2 y to the minus 1/2. So we've got to be very careful, but what function has the derivative? What is the derivative of b? It should just be c times this thing over here evaluated at square root of y, right? Because the whole thing is b is the antiderivative of what's inside. It's just going to be c e to the negative, oh, life is good, right? We have a negative square root of y squared, that's e to the negative y over 2, and then we put in square root of y, so we would get y to the n minus 1 over 2, right? And then we have a 1/2 y to the minus 1/2. So that's going to just be c over 2, y to the n halves minus 1, the minus 1/2 and the minus 1/2 gives us a minus 1, e to the minus y over 2. Ooh, what is that over there?
That's the chi-squared.
That's the chi-squared with n degrees of freedom. So that's another direct proof of that. So we've got the chi-squared with n degrees of freedom. Now, how is this useful to us? We actually know how to integrate the chi-squared distribution with n degrees of freedom. And we know what all the normalization constants are. Right? We can use this now to calculate the surface area of a sphere. Because this surface area, when I calculate this integral over here, that's going to just be the surface area. And then the rest of the R integration, we know how to do the R integration here. So we can actually write this as this thing over here is the surface area when I calculate that. And if I take R equals to 1, it's the surface area when the sphere has radius 1. It rescales in a very nice way. The details are in the book. But if I actually was a little bit more careful with what this constant c is, I can actually write that constant as the surface area with a 2 pi to the n halves in the denominator. And now if I integrate this whole thing from 0 to infinity, I know I get 1. And then that will give me a formula for the surface area. It'll bring like the 2 pi to the n halves over to the other side. You'll have gamma factors coming from this. So when the dust settles, you can actually get the formula for the surface area of the n-sphere. And if you want with a little bit more work, you can also get the volume. So this is one of the remarkable applications of chi-squared random variables. It's, I think, the only way I really know to easily calculate the surface area and the volume of the n-sphere. And what I will end with today is circle pi r squared, 2 pi r, sphere, 4/3 pi r cubed, 4 pi r squared. The area of the circle, its derivative is the perimeter. The volume of the sphere, its derivative is the surface area. And you can see this by taking a circle, and if you expand it a little bit, what is the width, or what is that area of that little ring? It's approximately the perimeter times the thickness. And the geometry is really nice. You only have to learn half the formulas. You get the other formulas from differentiating. All right. This was a lot today. This was piling all the stuff on. You are not expected to have this memorized. You are not expected to be able to reproduce this. All exams are open book. I want you to be aware of this stuff. And so rather than having this spread out through multiple lectures, let's just concentrate do it all at once and get it over with. And I'm happy to chat, but really just look at this and see how we are able to handle these problems in a tremendous way. That we can bypass these integrations. We don't even write down what the spherical coordinates are. That's absurd. If you're doing an integration in n-dimensional spherical coordinates, step 1, write down the spherical coordinates. So it's really worth pondering why we're able to succeed. The power of the normalization constant. All right. Yes.